Discovered by chance at the beginning of the 20th century, it remained unfinished and, in part, misinterpreted by generations. For over 100 years, an enigmatic item fascinated researchers: the so-called Antikythera mechanism, considered the initial analog computer of history. It was known to be capable of anticipating celestial events, such as eclipses and lunar phases. However, half of its framework had been lost on the ocean floor, creating fundamental gaps in its interpretation. But before we begin, don't forget to like and subscribe to our channel. The discovery began in 1900 when sponge hunters, under the command of Dimitrios Kondos, forced to seek shelter on the island of Antikythera between Crete and the Peloponnese, due to a storm. Upon descending approximately 45 meters, Elias Stadiatis came across what he thought was a pile of corpses. In reality, it was a collection of metal sculptures from an old naval disaster. At that moment, one of the pioneering structured underwater searches in history began, with the support of the Greek Navy. Among the various items recovered, there was a worn piece of metal and plant matter that initially did not attract attention. It was only in 1902 that the researcher Valerio Stais noticed a cogwheel in that piece, revealing something phenomenal. This item, later named the Antikythera mechanism, was estimated to be over 2 millennia old, even predating the ship that carried it. Currently, there are only 82 pieces, about a third of the original, housing nearly 30 connected metal gears, some with hundreds of intricately hand-carved points. For decades, scientists have tried to understand how it works. Significant advances occurred from the 1970s onwards with X-ray studies, but it was in 2005 that an international team used advanced technology to investigate the object more thoroughly. A high-powered computed tomography scanner allowed them to visualize the interior of the parts, while a digital lighting system revealed almost invisible inscriptions. For the first time, the mechanism spoke again, showing instructions engraved on its surface. These analyses revealed that the device was extremely sophisticated, capable of representing complex astronomical cycles. On the reverse, one of the dials indicated the 19-year Metonic cycle, equivalent to 235 lunar months, used to align calendars with the seasons. Another dial marked a larger 76-year cycle, further refining the precision. These details confirmed that the ancient Greeks possessed a much more advanced level of technical knowledge than previously imagined. Technical problems during the initial scans made a complete reading difficult, but in 2018 the data was reprocessed with greater precision. New letters emerged, correcting previous interpretations and helping to reconstruct lost parts of the mechanism. With the aid of artificial intelligence, it was possible to restore inscriptions and propose more complete models of the device. Today, the Antikythera mechanism is seen as an impressive testament to human ingenuity in antiquity. A device so advanced that it wouldn't have equivalents again for over 2,000 years. Even so, it continues to hold secrets, reminding us that even the greatest advances of the past can remain partially hidden, waiting for the right tools to be fully understood. The lower half features another spiral with 223 lunar months, the Saros cycle, famous for predicting eclipses. Inserted within it is a smaller dial that tracks the exoligmo, a triple Saros cycle of 54 years that corrects for the troublesome 8-hour excess in each cycle, ensuring that the timing of eclipses remains accurate. Another small dial marks 4-year intervals for the Great Pan-Hellenic Games. None of this is speculation. These functions are inscribed in bronze. By bringing your gaze closer to the Saros spiral, the mechanism becomes surprisingly practical. Each cell that can contain an eclipse carries a small glyph, a compact note in Greek. A letter indicates whether it is lunar or solar, sigma for Selene, the moon, or eta for Helios, the sun, a symbol resembling an anchor Actually, a ligature of omega and ROE signifies hour, followed by a letter number indicating the time. Expressions such as of the day or of the night indicate whether an eclipse would be visible from Greece. Below each glyph is an index letter pointing to a block of explanatory text. These texts describe details such as the direction from which the shadow would fall, how much of the sun or moon would be covered, and even indications of colors that could be observed. Imagine a user turning the crank to a specific month, watching the dial indicate an eclipse, and then reading the type, time, and full description. For a device from the 1st century BCE, that's impressive. The inscriptions also reveal a cultural marker. In 2008, a large study of the reverse text identified the complete set of month names on the Metonic dial. They did not correspond to the known Athenian calendar. Instead, they belong to the Corinthian calendar family used in Western Greece, especially in Epirus and Corcyra. Today, scholars believe the sequence best fits the Epirate calendar, possibly linked to the colony of Ambracia. Calendars are cultural markers. By engraving these month names, the maker essentially signed off on the device's civic identity. The front part of the mechanism is much less complete. The gears and plates that once protruded from the main structure have disappeared, leaving only fragments of the cover plates. Even so, these covers were inscribed, and their surviving lines are valuable. In 2016, researchers published a critical edition of what they called the front cover inscription. These texts are not poetic riddles. They are lists of precise planetary relationships for each of the 5 known planets: Mercury, Venus, Mars, Jupiter, and Saturn. The inscription details how many synodic cycles or phase returns relative to the Sun equate to whole numbers of years and complete revolutions through the zodiac. In simple terms, the lid establishes the whole number ratios that the missing gear trains needed to reproduce. When it states that after a certain number of years a planet completes a precise number of synodic cycles and zodiacal revolutions, this is not a suggestion. It's a requirement. Any reconstruction of the front section must meet these proportions. That's what makes the missing half such a big challenge. We cannot simply imagine any model of the sky. The preserved gears show what techniques the builders used. The inscriptions determine which mathematical periods should appear, and the physical space available in front of the structure imposes strict limits on how many wheels and pipes could fit without colliding. A viable reconstruction needs to simultaneously satisfy these 3 constraints: mechanical, mathematical, and spatial. And that's where the real challenge begins: reconstructing the lost front and proving that it could actually function. The reconstruction of the missing front half of the Antikythera mechanism was not done by guesswork, but through careful engineering. Step by step, the researchers took the established facts, number of gears, tooth size, surviving inscriptions, and the bronze structure itself, and used them as a basis to build the part that no longer exists. And even before the gears were reconstructed, artificial intelligence gave the researchers a head start. A model called Ithaca, created by DeepMind, helps restore damaged Greek inscriptions. On its own, it predicts missing letters with about 62% accuracy. But when used in conjunction with human historians, it raises that accuracy from about 25% to over 70%. This is important because the numbers engraved on the cover plates are exactly the targets the front needs to hit. Cleaner, more confident readings narrow down design options, reducing uncertainty and narrowing the path forward. The first person who truly proved that the front end could be more than just a theoretical exercise was Michael T. Wright. In the early 2000s, Wright, then curator of the Science Museum in London, built functional models by hand. He introduced epicyclic gears, small gears mounted on arms that orbit around larger gears, to capture the non-uniform motion of the planets. He also used the pin and slot mechanism, an ingenious system in which a pin moving within a groove forces the follower gear to accelerate and decelerate smoothly. Ancient Greek astronomers had already anticipated this type of irregular motion, as the planets appear to change speed in the sky. Wright went so far as to build a complete planetarium model long before the inscriptions on the lid were fully deciphered. Was his model perfect? No. But he demonstrated, in solid brass, that the front panel could, in fact, represent planetary movements using techniques compatible with the technology of ancient Greece. Their models shifted the debate from maybe to yes, this is possible. Subsequent teams built firmly on this foundation. The decisive leap came in 2021 when a team from the University College London presented what they called the Cosmos model. It wasn't just a pretty drawing or a computer animation. It was a complete architectural front facade that had to adhere to strict rules. It had to fit within the available physical spaces of the surviving structure. It needed to reproduce exactly the relationships of entire periods recorded in the inscriptions, and it had to allow shafts and tubes to pass through the center without colliding. At the heart of this project is a small dome representing the Earth and the Moon system. Around this core, the planetary gear trains are arranged so that their outputs feed a set of thin, concentric tubes in the center. The researchers called this set the Central Coaxial Output, or CCO, and it is the backbone of the entire system. It allows multiple dials to share the same axis without interfering with each other. The face of the mechanism in this reconstruction is organized into concentric rings rather than several overlapping pointers. This may seem purely aesthetic, but it is essential. The rings reduce parallax problems, making it easier to read and correspond to what the user manual describes about a cosmos organized in rings. One of the smartest decisions was to reposition the initial drive gears for the Sun and the three outer planets, Mars, Jupiter, and Saturn. Previous reconstructions placed these gears behind the large circular plate called CP in the study. This choice always generated difficulties. To circumvent the problem, complex supports were needed, which increased the volume and were unlikely for older builders. The UCL team solved this by moving these gears forward. This single change freed up space, eliminated the need for complicated supports, and gave each planetary system a direct path to the central output. At the exact center, there is a fixed gear, identified as 56 in the study, and compact epicyclic assemblies rotate around this point. This type of solution only emerges after numerous failed layout tests until, suddenly, everything fits together. Part of what makes this design elegant is the sharing of gears. Instead of designing each planet from scratch, the UCL team had several systems share key components. The True Sun shares a gear, identified as 52 with Saturn, and uses the same fixed gear, 56, that supports all the upper planets. Mars and Jupiter share another gear, identified as 64. This type of economy is essential when available space is extremely limited. Each additional shaft increases thickness, and each new gear can cause interference. By sharing components, the model remains compact and functional. The reconstruction also had to respect a detail preserved in a large fragment: the main drive wheel with 4 spokes and sets of pillars around its rim. These pillars supported 2 plates, a rectangular strip mounted on shorter pillars and the circular CP plate mounted on longer pillars. The UCL project uses this structure as a sandwich. Between the main wheel and the track, they accommodated 9 layers of gears in a space of about 1.5 centimeters. This compact area houses the Sun's mean motion, the lunar node mechanism, and the basis of the inner planet systems. Between the track and the CP, They concentrated most of the gearwork of the Sun and outer planets in a space of just 9.7 millimeters, about 0.97 centimeters. The fact that the bar is angled at 11 degrees relative to the radii is not a mistake, it's an advantage. This angle gives Mercury and Venus enough space for their epicyclic parts to pass through neighboring components. It's a level of compactness worthy of watchmaking, measured in fractions of a centimeter. One of the most satisfying moments of investigation in this reconstruction comes from a small block in radius d that has a mysterious hole running through it. For years, no one could explain its function. The architecture of 2021 solved this enigma. The small, half-black, half-white sphere on the front of the moon needs to receive information from both the Sun and the Moon to correctly display the phases. But if the front face is constructed of rings, it doesn't make sense to duplicate the Sun's calculation just to feed the lunar mechanism. The UCL design directs an average movement of the Sun through a bar connected to this perforated block at radius d, forming the shortest bridge over the fixed central gears until it reaches the lunar phase device. Suddenly, the block ceases to be a mystery and becomes a support with a well-defined function. The Venusian mechanism offers another revealing moment. A small fragment, called Fragment D, preserves a disc riveted to a gear with an axis that changes shape from square to circular as it passes through a plate. The gear has 63 teeth, with all but 3 still intact, which guarantees the count. In the UCL model, this disc carries the offset pin necessary for a pin-and-slot follower to generate Venus's erratic motion. The plate becomes the bearing surface at the exact height. The fit is so precise that the authors argue that the pieces of Fragment D form the epicyclic core of the Venus system. Regardless of whether one considers Venus's role on the dial important, the point is clear. The surviving bronze fragments are exactly where the mechanics require them. A similar discovery occurs on Ray B, which has an evident support with no clear function in previous reconstructions. In the 2021 design, this support holds a compact epicyclic set of 4 gears for the lunar nodes, the variable line that marks where the Moon's orbit intersects the Sun's path. The alignment of this support perfectly matches the size of the teeth in the model, and the available space is exactly what is needed for this system. There is also an honest simplicity in the gear count. Behind the rear plate, the preserved systems already total 35 gears. The 2021 model adds another 34 gears to the front to represent the cosmos. In total, there are 69 gears. This number is compact enough to fit within the preserved bronze structure and specific enough to allow listing the number of teeth and the position of each gear. Internally, the designers kept each planetary system as lean as possible within the mathematical requirements. The real Sun uses only 3 gears. Each outer planet, Mars, Jupiter, and Saturn, operates with a compact epicyclic set of 7 gears. The inner planets, Mercury and Venus, utilize 5-gear systems with pin and slot mechanisms to reproduce their characteristic acceleration and deceleration motion. When the central system needs an extra transmission but the shaft is blocked by fixed gears, the team uses a perforated block and a crossbar to bypass the obstacle, as is the case with the bar on the average Sun at radius d. These are small but essential solutions that real mechanisms require. What makes this 2021 reconstruction reliable is that it can be tested. In 2025, another research team tested the model through computer simulations. They used triangular gear teeth, the pointed style common in modern replicas, and added small manufacturing errors to observe the result. The results were a warning. The shape of the teeth by itself wasn't a major problem, but if the spacing between the gears was incorrect, even slightly, as was sometimes suggested, the system could seize up after prolonged use. This doesn't mean the 2021 model is wrong, but it raises more difficult questions. What kind of teeth did the Greeks actually use? How precise were the measurements? How smooth was the bronze finish? The main point is that this is no longer just a historical hypothesis. We are now dealing with real engineering problems, such as friction, alignment, and wear. Problems that can be measured and tested. Now that the reconstruction works on paper and in simulation, we can finally ask the most important question. What did the Greeks really see when this machine came to life? The first thing you would see is the center, a small dome representing the Earth. Around it, a pointer shows the position of the moon as it moves through the signs of the zodiac. Next to this pointer is a small sphere, half black and half white. Day after day, this sphere rotates to show the phases of the moon. When it is completely dark, it is a new moon. When it is fully illuminated, it is a full moon. Each intermediate shade appears in this small sphere, but the moon is only the beginning. Around it, 6 thin rings are arranged, each representing one of the celestial bodies observed by the Greeks: Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Further out is the Great Circle of the Zodiac, divided into 12 signs, and beyond it, a ring that shows the days of the annual calendar. Each planet is indicated by a fixed marker on its ring. The Sun receives a golden marker with its own pointer, exactly as described in ancient inscriptions, which speak of a cosmos organized in rings with small spheres. On the outermost edge, a narrow ring indicates the date. If you want to know the day, just read there. If you want to see where the planets are in the sky, just look at the markers. None of this is speculation. Inscriptions discovered in 2016 describe the front face in exactly these terms, and the 2021 reconstruction followed these descriptions closely. Together, they confirm that this front face displayed 9 elements simultaneously: the Moon, the lunar nodes, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and the calendar date. Starting with the Moon, which is the heart of the sky. The moon pointer shows its position in the zodiac, allowing you to know exactly where it is among the constellations on any given night. The mechanism also allows you to see the age of the moon, that is, the number of days since the last new moon. This is determined by comparing the moon's position with that of the sun on the dial. The difference between the two indicates the lunar age. Cicero once described a bronze machine that caused the moon to lag behind the sun by the number of days it lags behind in the sky. This same principle is incorporated into this device. The moon follows the sun, day after day, across the face of the mechanism. Then comes the sun. Its golden marker travels along the zodiac ring throughout the year. When it crosses the first degree of Aries, spring begins. When it reaches Cancer, the summer solstice occurs. In Capricorn, the winter solstice. In Libra, the autumn equinox. All of this can be seen quickly. The inscriptions also mention a ray associated with the sun, representing its intense brightness in the sky, the same one that obscures the planets when they pass too close. The 2021 reconstruction included this golden marker. Given this mechanism, a calendar is unnecessary. The position of the sun alone indicates the season. Each planet tells its own story within its own ring, and these stories are not abstract. They are the same events that interested ancient observers. Each ring has markings for phenomena such as conjunctions, when a planet is obscured by the sun's glare. Oppositions occur when outer planets are opposite the sun and appear in the sky when the sun sets. Maximum elongations occur when Mercury or Venus reach their greatest angular distance from the sun in the sky at dawn or dusk. And the seasons are the points at which a planet appears to stop and reverse its movement relative to the stars. The inscriptions show that the zodiacal scale had small indicator letters for these events, and the 2021 reconstruction expanded this idea to the planetary rings. On the ring of Mars, for example, there is the opposition mark. On that of Venus, the elongation mark. When the marker reaches these points, it's possible to identify the phase of the planet's cycle. There's even a special pointer that doesn't represent a planet. It is a long, serpent-like pointer called the dragon pointer. It tracks the moon's nodes, the points where the lunar orbit intersects the sun's path. Ancient astronomers often described eclipses as a dragon swallowing the sun. In this mechanism, the dragon's pointer moves slowly through the zodiac. When it passes under the sun marker and enters the triangular windows of the dial, it indicates that the eclipse season has begun. Eclipses can only occur when the sun is near the nodes, approximately twice a year, and these seasons are indicated directly on the dial. The dragon's hand completes a revolution in about 18.5 years. This cycle is incorporated into the mechanism. No fragment of this pointer has been found, but the integration between the front and back parts makes its existence evident. The dial also functions as a calendar. Around the movable rings are two fixed scales, the zodiac with its 12 signs and the date ring with the days of the year. Small indicator letters appear along the zodiac. Each one corresponds to a line in rectangular panels positioned above and below the dial. These panels contain the parapegma, an ancient list of seasonal celestial events such as the heliacal rising of a star or the disappearance of a constellation at dusk. Farmers, sailors, and travelers relied on these signs. The 2016 edition identified 42 entries throughout the year. To use it, simply check the position of the sun. If the marker is on a degree marked with a letter, such as K, simply consult the corresponding panel. This line will indicate which star should appear or disappear during that period. The mechanism and panels were designed to be used together. But how would anyone actually use this machine? First, you adjust the date ring to align the calendar with the zodiac and turn the crank to the desired day. From there, the reading is straightforward. The gold marker indicates the sun. The small sphere shows the phase of the moon, and its pointer reveals its position in the zodiac. The planets appear with their own markers, while the markings indicate the phases of their cycles. When the dragon's pointer coincides with the sun in the triangular areas, the eclipse season begins. If the sun is over a letter, simply consult the parapegma to identify the corresponding celestial event. In a single glance, the entire sky can be interpreted. To make it easier to read, the designers used different colors and sizes: the sun in gold, Venus in deep blue, and Mercury in turquoise, avoiding confusion with the sun's glare. The moon, although small, is visible enough to follow its changes. With 9 elements in simultaneous motion, the system reveals different rhythms. Saturn advances slowly, Jupiter follows long cycles, and Mars stands out, especially at opposition, when it appears opposite the sun and brightest, something reflected on the dial. Venus and Mercury remain close to the sun, with their most striking moments at maximum elongation, visible at dawn or dusk. Now, check out the videos on the screen to explore more amazing stories.